Scutosaurus lived during the late Permian and was one of the first large-bodied herbivores to evolve on land. Essentially, 100 million years earlier during the Devonian, when animals first started to move onto land, they were, as far as we can tell, pretty much all carnivorous. But eventually, during the early Permian, animals like Edaphosaurus started to achieve moderately large sizes on land while being herbivores. And Edaphosaurus would have been about 10 feet long, or around 3 meters, but it was still very lowly built, not quite the kind of massive animal that Scutosaurus was. And Scutosaurus was able to become the more dominant herbivore because of the massive faunal change that happened during the Middle Permian. And this was throughout the environment, with predators like Dimetrodon and Sphenacodon being replaced by the Theraspids, some of which would actually evolve into mammals. And the largest herbivores, like Edaphosaurus, were replaced by the Parasaurs, which does include Scutosaurus. And these were bulkier animals, with odd heads and bony osteoderms throughout their skin, along with cusped teeth to help process plant material and a very wide gut to also help process that material. But what the hell were they? Well, if you've seen my other videos about odd Permian and Triassic animals, you know that I'm going to mention how many holes are in the head, and specifically in the temporal bone on the head. And that's because in synapsids, which are related to mammals and include the other animals like Edaphosaurus that I mentioned earlier, they only have one opening in the temporal bone for muscles to attach to the lower jaw. Meanwhile, in diapsids, which led to modern day reptiles, there's two holes in the temporal bone. And so when we look very closely at Scutosaurus' skull, what we see in the temporal bone is that there's absolutely no holes in the skull like this. So Scutosaurus didn't have any fenestra on the temporal bone, and this is incredibly strange. Essentially, the one major feature we use to identify most fossils in the fossil record as being either mammaline or reptiline is completely absent in Scutosaurus. And actually, there's only one other group that's really well known in the modern day for not having any of these temporal fenestra. And I will get to them later because they may or may not have anything to do with Scutosaurus at all. But for animals that do have something to do with Scutosaurus, we can look at some of its closest relatives in the larger group, Parareptilia. The Parareptilians were a pretty diverse group, with some animals like the mesosaurs going back to the water, as well as having some animals become bipedal, and of course having massive herbivores like Scutosaurus. Despite being called parareptiles though, they were actual reptiles, at least as far as we can tell. And the main reason we're able to tell this is by going further back into the fossil record, where we see some of the first members of Parareptilia actually having these fenestra, these holes in the temporal bone. And this is actually a lot in line, especially based on the size of the temporal bones, with some of the first of the other lineage of diapsids, and that's the Neo-Diapsida. And that would lead to all modern reptiles, with one possible exception that I alluded to earlier. This means there was two distinct lineages of reptiles evolving alongside each other for millions of years. And eventually, at least, the parareptiles would go extinct at the end of the Triassic. However, up until that point, they were pretty successful, including the largest herbivores on the planet up until that point, in animals like Scutosaurus. But it's not just Scutosaurus, it's also its closest parasaur relatives, animals like Bradysaurus or Bunostegos, the latter of which was actually one of the first known animals in the fossil record to actually be able to stand upright. But despite that gait, they still died out during the end Permian extinction. And this extinction happened because climate change killed off a lot of the plants. And so even the upright and well-protected and armored bodies of animals like Scutosaurus just couldn't find enough to eat. And as for what they were trying to protect themselves from, there's essentially two ideas. The first is based around the head, and the fact that it had so many different knobs, bumps, and other osteoderms on it might suggest that they were essentially headbutting and fighting against one another for competition within their own species. In fact, you can probably compare it to the Komodo dragon today, although with less fight hugging and more headbutting like I suggested earlier. In fact, if we want to expand this kind of comparison beyond just reptiles, we can probably look at deer, many of whom use antlers for combat within their own species even today, although Scutosaurus would have weighed a lot more than any modern deer because it probably weighed a lot closer to the weight of a modern day rhino, and that's largely due to the fact it had this massive gut. But also the additional bone mass and osteoderms on the back and sides also would have helped add to this weight. And these osteoderms would have been also for armor, and that brings up the second hypothesis for why they were so armored, and it's defense against predators, at least potentially. There were some large predators. Specifically, I already mentioned the Theraspids, and one group of them, the Gorgonopsids, became the largest predators on the planet during the late Permian. In fact, one of these, Inostrancevia, actually also comes from some parts of northern Russia, the same place that Scutosaurus has been found for. although eventually the Siberian traps, a set of massive volcanoes, would erupt, changing the climate and leading to the extinction of both of these species. But there was a group related to the Preosaurs that did survive this extinction, and those are the procolophids, which were relatively small, especially compared to the massive body sizes of the Preosaurs. And these animals were probably the only parareptilians to actually survive into the Triassic, although they did go extinct at the end of the Triassic. And I bring up the term "we're probably the only group to survive" because that one lone group that doesn't have fenestra that I mentioned earlier in this video may or may not be parareptilians. This group is actually really widespread today, occurring on every continent except Antarctica. And I actually had the opportunity to help catch some, including some invasive species like the red-eared slider. And if you don't know what a red-eared slider is, it's a species of turtle. Turtles have a kind of muddy origin story during the Triassic, when we believe they first evolved, at least based on fossils like Chinleychelys, one of the first known turtles in the fossil record. There's also other animals that may or may not be turtles, or may just be closely related to the turtles. However, based on morphology and morphology alone, so essentially just the shapes and features of the bones, turtles do align very well with the parareptilians, in part because of the anapsid, so fenestra less, or not having the holes in the temporal bone condition, and also because of those osteoderms and that armor plating that many of the Preosaurs actually had. But I want to be entirely clear that this is not a closed case. In fact, most researchers don't believe that turtles are very closely related to the Preosaurs or parareptiles at all. And that's because of genetic studies, which help to show that the turtles are closer genetically to things like alligators and birds than they are to lizards. And this would place turtles firmly within the neodiapsids, which I mentioned earlier. And that's because essentially both of those groups, the lizards and the crocodilians, would have to branch off from one another. But then on the lineage that would also lead to things like the crocodilians, there would be another branch which would lead to the turtles. This means that the turtles would absolutely be neodiapsidans, and this is what's generally accepted by most researchers today. And this kind of placement within the archosauriform reptiles that would eventually lead to the crocodilians is where most researchers would place the turtles today. And that's because if there was the actual genetic evidence that they were parareptilians, we would expect the turtles to be equally distant from both the lizards and the crocodilians, rather than closer to one or the other. But like I mentioned, there's still a lot of debate. In fact, a paper just this past April looked at Chinleychelys, one of those early turtles that I mentioned, and did find it to actually be sister groups, so right next to animals like Scutosaurus and Bradysaurus. The authors also point out that in the archosauriforms, there's not really any animals that seem to be really good candidates for stem or early turtles, or even relatives to those early turtles. Instead, the turtles, under that idea, essentially just show up out of nowhere. Meanwhile, when we look at the Preosaurs, they do line up very well, at least as far as morphology is concerned. The authors also point at genetic convergence as a possible factor. Essentially, the idea that genetically different features evolved convergently in both crocodilians and in the turtles, making them appear more closely related than they actually might be. That said, it's going to be really hard to try and prove that. Genetic evidence is generally pretty reliable, and so the turtles may or may not be Preosaurs. However, if they are, that means that one of the most common groups across all of the continents today may actually have its origins as the last of a long lineage of parareptilians.